Okay, I guess we can start. So I would first like to welcome everyone who has joined this call, and also welcome already the people who will still join. A very warm welcome to this new Mind Technical Talk. It's been a while since the last technical talk. It's been a very quiet summer, but we are resuming our activities. A first announcement is that we will have a new blog post coming up. It's currently under review. It's about Doom and how to play the game Doom on an embedded device. I believe that's a very exciting topic. So that will be published, let's say next week. Looking at what you probably next week. There we go. And then at the same time, resuming our activities with a Mind Technical Talk, which today is presented by 4 different people. Arnout, who we all know very well, and then Charles-Antoine, Thomas, and Titouan, who have visited Amsterdam about a week ago, where we had the Open Source Summer Summit. And we had also a few satellite meetings, such as a Buildroot developers meeting. So there's been a lot of activity, and Arnout, Charles-Antoine, Thomas, and Titouan are going to present the most important and key takeaways from those meetings. So that's it. You guys can go.
Yeah. Yeah, you already introduced a bit the summit. So the Open Source Summit is actually like a constellation of multiple conferences around it. Like the most important one for us is the Linux conference and the Zephyr Developer Summit. So there are actually other tracks that we care a bit less, maybe here at mine, like things about cloud and that type of stuff. We did have some interest going over there because people like yeah, the microphone is actually quite close, so
speak louder.
Yeah, I will speak louder then. We had some interest over there because Titouan was doing a presentation over there, and I had to attend the Buildroot developer meeting that was just after the Open Source Summit. So it was a good occasion for us to also visit the conference, and Charles-Antoine also visited us. So yeah, it was also a good occasion to get a bit of the feel of the latest trend, latest news, new things, new developments in industries. But yeah, Charles-Antoine will start talking about some of the things he likes.
So I will talk about 3 different conferences related to Yocto and a bit about CRA or security issues. 2 of them took place during the extra day dedicated to Yocto. In fact, it was a day with a lot of conferences along the day, with the opportunity to discuss with Yocto developers. And the first conference took place during the main open source summit with other topics in parallel. So I will start with this one to produce, in fact, Yocto image in a single command. In fact, the context is building Yocto image for the first time is always a bit difficult because you have to download a lot of layers from different sources. You have to set up some different variables which are mandatory to start the build, and also you need to execute a script to finalize a setup. But in fact, each vendor, Yocto and other tools are doing this step in different way with different methods, and in fact, it's quite a mess, and it can be difficult also to integrate it in a continuous integration system and being easy to use also for developers in parallel with the same source tree. So the idea is to try to solve this issue by providing a specific tool which can try to simplify this workflow. So the idea is to introduce a new command, bitbake setup, which can be run in interactive and non-interactive mode to be integrated, to be easy to use for new users, but also easy to integrate in continuous integration system and so on, and for already developers of Yocto. Also, the idea is starting to ask questions about to set up the distros, the machines, the configs that you want to run. Also, you have a JSON file with a list of layers to download, and bitbake will take care of downloading them and updating them if needed. So the idea is really to do this step in an easy way and a standard way for everybody. But in addition to add this tool is the momentum to, in fact, refactor a bit the configuration of Yocto, because everything is put in general in local.conf file, but it's difficult to maintain if you want to have a specific config for continuous integration system, some config for other developers, etc. So the idea is to split some of these variables into different locations, which is easier to maintain and to select the right one for the right purpose. So that's a reason also to not use CAS, for example, to do this step, because it was the momentum to refactor a bit Yocto for this. And also he mentioned the difficulty to integrate CAS as it in a Yocto source suite. But so the work is still in development, and feedback are welcome to polish it and to improve it in the future as well. The next conference is about using Yocto to generate SBOM in a CLA context. In fact, the title is a bit misleading because Yocto is already mostly compliant with CLA to at least produce reports. But the idea is the US administration can have stronger requirements for some things related to SBOM. And the question is, if the CLA in the future will require the same thing, Yocto is compatible or not with these extra requirements. So he made a big list of what is implemented by Yocto or not. I will not cover all of them. Here you have in the presentation at least some options to be able to generate the report, to have the list of CVs against your firmware and the list of software included in your firmware in a standard format. It's very easy to use. You can do it right now if you want. It's not a problem. But if we want to have stronger requirements around it, there are some missing steps. In fact, it's mostly, okay, we have the information, but it's not complete, or we should add more metadata about it. Like, for example, the author list, which is in general very limited. They want a complete list of authors. Sometimes you can have legal entities like a foundation or a company behind a component. So the idea is to have the name of this legal entity and a way to contact them if needed. Also, being able to provide some extra information about a component. Is it an archive, a library, a binary, etc. And when you are building the component, at this moment, we can have sometimes the hash of the source code, but without the extra patches provided by Yocto or yourself. And in fact, they wanted a way to provide the hash, including these extra patches. And some other requirements are not, in fact, out of scope of Yocto, like, yeah, okay, you are making a list of firmware and packages. You have to deploy them somewhere. The US administration can require to have the list of link to these resources, but it depends where you are hosting them. So Yocto will not take care of that. And also signing the final SBOM. During the conference, he also mentioned some commands and steps to generate part of the final SBOM also. So if you are interested in, you can look at the slides of this presentation. It was interesting. The last conference about Yocto mentioned today is about, in fact, in CRA context as well for the security issues in the kernel. The idea is the kernel has a lot of CVEs, in fact, and a lot of releases on a weekly basis in general. So it can be difficult to follow the updates and or to backport all of these patches manually and check against regressions if the kernel can run on your hardware or not correctly. So the idea is to try to find out compromise. Okay, the kernel is a big binary which is doing a lot of things, but in fact you can configure a lot of things, and a lot of things are not in your final image, in fact, because you are not enabling all drivers, etc. So the idea is to use this information to just check if some CVEs are in your firmware or not. And I will not go into the details of these commands, but you can execute them if you want to produce the report. The idea is to, in fact, compile the kernel with debug information, to have the list of files which are used to generate the final library. And with some options and some scripts, you can extract the information from the binary, removing in the source list those who are not included in the binary. And the kernel.org is providing some metadata, in fact, to know for a specific CVE where it's come from. Is it coming from a specific function, a specific file, or is more generic than that? And in that case, you can check without using only the version range of the CVE if you are impacted or not by this specific CVE. And he made a demonstration for a realistic case. In fact, it dropped a lot the number of CVEs which can impact a specific firmware, which can be an interesting way to avoid to backport patches or nothing, and sometimes just to be sure, okay, there is a new CVE, is it a problem for me or not? No, okay, so I don't have to make a new build soon just to fix that because it doesn't affect me. So that can be interesting for that. This work is already available in latest version of Yocto. It can be used for other recipes with some works, but the main issue is to provide, in fact, the metadata required to know, okay, this CVE is for this file or this function, and making the mapping. But it's technically doable. So that's it for me. Thomas will talk about Perl.
Yeah. Perl PURL, not the language. What is Perl? It's a standard basically for package identification, like for ecosystem. So if you know like a CPE to match a package to CVE, for instance, it's something that is quite similar, but I think the idea is more to have kind of a canvas that can be automated for packages that you can directly assign a Perl to a package instead of having to find out which CPE match a package by yourself. So the image was not there, but the text was the same. So my interest in going into that conference was because I did some work to try to integrate Perl into the Buildroot project. So I was interested to see what that guy had to say, and apparently I didn't know that the guy was the guy behind Perl, the creator of Perl. So he had a lot to say and present all the tools that's already use Perl and that you can use if you use Perl to match dependency to your packages, or to also try to do dependency analysis of your package. So a lot of databases are freely available and already usable. But the main takeaway I take from this conference is that Perl is coming to the next CVE schema. So the idea is that you can directly add a Perl that you can compare to the package Perl to find out if CVE is vulnerable to your package. And also the main problem that Perl has right now is that it's really bound to a specific ecosystem. So for instance, let's say PyPy or Crates for Python or Rust. There are ecosystems where you can already not have a clash naming of the packages. So it's quite easy to match a name to a package in that same ecosystem. But most of the software that are running on your computer are mainly C or C++ packages. And for them, there is not a well-defined ecosystem that is present. So you can have software that has the same name and you can really match them. So they are actually working on providing those type of identification for C and C++ packages. So it's a big step forward to the adaptation of Perl and working with them, because it will enable us to match a lot more software to the vulnerability quite more easily than the CPU proves. A second tool I want to discuss with, it's more of a general overview type of talk. So I really like this type of talk because it gives you a good introduction to a lot of subject and lets you actually dig a bit deeper into the subject if you want to find more information about it. So the main point of the talk is what can you do if you have a sudden loss of power to avoid corrupting your file system and not being able to boot. So for this, the speaker actually try to split it into different category of things you can do. But every improvement you will do will kind of have a detriment in another category. So if you want to improve the performance of the file system, of course, you will reduce the flash longevity or the reliability of the overall file system. Price can be also a factor, but it's a bit apart. And of course, in the scope of that presentation, the main one was to improve the reliability. But in that, if you want to improve reliability, of course, performance will be degraded a bit, and flash longevity may also be impacted. For this, he structured his presentation into 3 main levels. So the first one was the hardware level. Some of the things he suggested were kind of obvious. So adding a supercapacitor or battery to be able to run some operation on sudden power failure. Usage of PMIC, but also some of them that were interesting is also like the main takeaway is to always check the datasheet of your eMMC or flash storage, because you can already have some of the features that are embedded that you can actually use. So some of them is to disable the device cache to avoid some of that data power is lost. Also, enhanced area nodes that you mentioned, or where to available, which are some features that are persistent. So if you enable, you can disable in the future. For the OS level, it is kind of an overview of the different file systems and their advantage. So yeah, it was really interesting if you want to leave a look, but it also gives good, yeah, good key on how to then partition, also providing over provisioning. So leaving a part of the flash not partitioned so that the actual controller can do some some performance based, some improvement on that non-assigned flash to cache field or in the account. At the application level, you mentioned the systemd hook key power to run some hooks when you have a power failure, or atomic read write with a basic move of a file to be sure that it will be in a consistent state. Also suggested to always monitor any reviews. And the last talk I want to talk about is about measuring the impact of secure boot in your embedded system. So it was more of a hobby style project or research style project, not really a professional use case for the speaker, but he wanted to see what improvement it can bring to an embedded device that has secure boot to reduce the overall boot time. He spent quite a lot of time explaining how we did the measurements for this presentation. I tried to put the main point where where the secure boots actually increase the boot time. So mainly it was coming from the user space startup, and in the kernel loading also you have like 100 milliseconds of increase, and mainly come from the increased size of the kernel because of adding the from first to set up the encrypted partition. So the star of the show in the presentation was the RS init program that he did. So basically it was a replacement for an neutral-FS image. So it was a Rust program that he made that would just, for the sole purpose was to configure the encrypted partition and install the kernel. So instead of relying on the neutral-FS to do all this work and having to embed all those blocks in this library, we managed to reduce the size from 2.5 megabytes to 50 kilobytes. So just because of that reduced size, the time spent in the bootloader and loading the kernel was reduced by 200 milliseconds. The next big thing that is a good takeaway from the talk was in certain boards in Linux, like Linux will be by default using a non-optimal SHA crypto. So I think his board was an INX, and it was using this SHA CAN implementation, which introduced quite a big overhead compared to just using the CPU or the generic implementation. So it was also possible to use that CAN implementation. I think I used the same, but I don't remember which one is the slowest, but I can correct it. But basically, there was also an implementation which was relying on the CPU, CPU instruction that was optimized for the set of operation, which only introduced a 40 millisecond overhead. So just by changing the crypto use to load the user space application, he managed to remove 500 milliseconds of time spent to load the user space. So quite a big improvement for an easy fix, and probably to carry other part of the application when it's run. So this was a good takeaway to always check the quick implementation of it, because the default might not be the best. Yeah, and overall, he managed to just have 200 milliseconds of overhead, so not much, in my opinion, but it was interesting to see, and the speaker wanted to dig a bit deeper into the detail of that project and try to get as low as possible. So I think he enjoyed it. Yeah, and I will give the hand to Titouan.
Yeah, so continuing forward into the bootloaders. So this was one of the presentations I found very interesting because the presenter shared some real world stories of what happened in bootloaders. So the presentation was organized into like 4 real world examples and how they could be either addressed or at least prevented or mitigated. So the first attack that was presented, if not really an attack, at least some vulnerability in the bootloader was so you know that in U-boot or other bootloaders, you have an environment. And in that environment, you can define the loading address of several components, such as the kernel or the entire fit image that you are going to boot. And so in that case, there was an injection of a wrong value inside the environment of U-boot, which meant that the system was jumping into an incorrect area. And so, yeah, there was quite a lot of funny memes inside the presentation. And so you see the one in the middle of the screen here. So basically, you have a whole secure boot chain, and just by writing something into the environment, you can simply bypass that. So in that particular example, it was not very dramatic because the rest of the boot chain was not verified, and it doesn't continue. And anyway, this jumped into a junk, and so this wasn't a real problem. But anyway, some mitigation that could be put in place here is that you can enable on ARM the memory protection using the MMU. And also, the highlight is that you must verify the environment. And possibly also, but even if that's no silver bullet, there's the possibility to introduce some stack checking to avoid jumping into undefined areas, I would say. And so you can put some canaries and other techniques introduced by the compiler. So yeah, that was the first attack. Main takeaway, don't rely on the environment on a mutable environment to boot. So we can go on to the next slide. So in that case, the second attack was in U-boot or possibly other bootloaders, the file system implementations such as ext, fat, or whatever are actually just almost copy-pasted from the Linux code base. And so, you introduce the file system code into the bootloader, then some vulnerabilities are found, patched in Linux, but never imported, or maybe too rarely, not often enough. And so, yeah, you can see where that leads. Any malicious inputs can be crafted to do pretty much whatever you want. The main takeaway from the presenter was actually there's quite no fuzzing test at all on this implementation. So be it the file system or the USB stack if you boot from an external media. And so he's actually introducing some fuzzing tests in the barebox bootloader to detect such cases. And in the slides, there was a nice overview of all the CVE that are currently affecting U-boot or barebox. Another, I would say, no, it was still on the same slide. If you can just go back one slide. Yeah, and another related attack was so the barebox environment can also be stored on a partition, and that partition can be identified in the GPT new partition table, I think. by a UID. So fun fact, if you want to have a UID for your file system, you can simply introduce that on the Wikipedia page, then declare its standards, and then use that UID to have your file system detected. And so in Bearbox, they introduced the fact that you can autoload the environment from a matching partition identified by the GPT UID. And again, this leads to the same kind of problem. So if you load an environment that's untrusted, then you can do pretty much what you want. And so the main takeaway here is that the boot state should be out of the environment. In Bearbox, they have a dedicated state, which is a different concept as the environment. And if you have a secure boot chain, you should never rely on external environment, so only on things that are built in at compile time. And so then we can move to the next slide, which is a bonus story, I would say. So the story was, I think it was Nintendo. If you have some provisioning in the factory, eventually you will need some secure boot as well to provision the device. So they have some SD or MMC card or something like that, which has a completely different software stack as the production one. So they flash the device and do stuff, and then at the end they dispose of the installation media in the garbage, even though they cracked it in the middle. But some people were able to recover those media, and then as this is a very specific software used internally, there's no real security analysis, and so this could be reversed, and the people could design some hijacks into the actual production device because they had some entry into the secure boot. So in the end, the conclusion from that talk are, first of all, it was a lot centered around Bearbox because that's what the presenter is a contributor to that project, and so he's kind of selling it as well. But in Bearbox, there's a thing called config insecure. And so if you enable that, you are actually giving you more convenient options. So you have more flexibility in the boot process, which is very useful if you are developing or trying to debug things. But also that's a marker that your boot is certainly not secure, and that if you want to go to a production device, probably you have to change something there. And a new thing that gets introduced in Bearbox now are the security policies. So it's a distinct menu config where you can actually select some options that are relevant to your particular use case. And then in the code itself, there are some hooks which allow to disable some feature at runtime depending on the policy. And there was a nice demo at the conference showcase where the guy had some device, and it just would insert a USB key containing a JSON NaNa token, and that would put the device under a different policy. And so, for instance, a policy would disable the usage of the keyboard. Another one would allow the loading of Doom on the bootloader and that kind of stuff. So definitely, it's like kind of aspect-oriented programming where you can insert some hooks based on the policy which is enabled on the device, either based on the hardware configuration like if use or other non-volatile memory, or some external media. So if you move to the next talk, actually this were two talks because it was on the third morning. There were two talks, just one whole way apart, and I found it interesting because they were pretty similar. It's all about the power management and optimization, both in Linux and on Zephyr. And so I try to have a comparison here because I think it's relevant to get them all. So when we talk about power management, really it's about turning off devices to save some current, either to have more battery life, which is, I think the most relevant use case. And in some cases, there are also some intermediate states, so you can not entirely turn off the device, only some subsystems, which, you have different levels of power savings. And ultimately, that's a trade-off because the most asleep is a device, the most time it will take to get back up to speed, to get back to a normal working state. And so ultimately, power management is always a trade-off between how much power you can save by turning off things and how much latency you would have when waking up the device. So going on to the next slide. So this was on the left on Linux from the point of view of a device driver implementer, as well as on the right for Zephyr. So on the left, you see it's a bootlin talk. So as usual, you have like the very detailed, intricate details about how to implement things and code examples. But in Linux, basically, if you write a device driver, you can add some PM ops, so power management, to your driver, which are either runtime suspend or runtime resume, and which is responsible to do something about your the power state of your device. And then callers or users of your drivers or dependent device might use the API you see on the bottom left, which is enable, disable, get, put. I will get back to get and put in a few minutes. And on the Zephyr side, it's a bit different, but basically you have to implement the function PM action. And that function gets enumerate the value, which is in which state you would want to put the device, or at least which transition you would like to make. So in Zephyr, it's in Linux you have suspend or resume. In Zephyr you have off, suspended, or active. But actually, in practice, I think we never go back to the off state, or maybe if you have just some very coarse device management, like on-off with the GPIO or stuff. But most of the time you are going to move between suspended and active. So going on to the next slide. If you want to implement that driver in Linux, you have to register the PM ops and enable them at the probe time. And in the Zephyr driver, you have to call PM device driver init. So it's a bit different there because in Linux you have the probe, which is dynamic. So if you either load a driver through the device tree, or if you get something that's detected dynamically through USB, PCI, or whatever enumerated bus. While on Zephyr, it's really like something that's compiled in and will be statically allocated, I would say. But apart from that, you can see it's very similar. It's just expressed a bit differently, but it's the kind of same concept. And if we go to the very last slide, so there's there are something in common between Zephyr and Linux. So in both of them are refcon based. So the principle of that get put I told a few slides earlier is that when you want to use a device or you have a device that depends on another device, like for instance, an I2C device depends on the I2C controller, then you are going to somehow reserve that device and say, I'm going to use it. And so you increment the ref count. And so as long as that ref count is about 0, it means that that device is being used and so should not be put into a suspended mode. And also you can see there's like the parent-child hierarchy. So if you have like, again, in the device tree, some I2C target device, which depends on the I2C controller, then there must be something to express that. So you have like you are not going to suspend the controller while the device is in use. A few things that are slightly different then, it's like in Linux you have the auto suspend, which is you can tell the device to suspend a bit later, which is useful, for instance, if you need to send some commands over I2C, let them execute and then go back to sleep. And the power domains, which are actually, I don't know why I put them in the 2 columns because they are also in Zephyr, so that's an error from my side. but this wasn't presented in the Zephyr presentation. But again, you can group some device that shares, some, for instance, a common voltage regulator or that kind of things into a power domain, so you can turn off an entire group of devices together. In the Zephyr side, the presentation showed the device tree representation of power states. So you can enumerate which are the different power states you can put your device on or off, and the latency that's expected to put that device back on. And that helps the scheduler to choose which power state it will use. And finally, there's a distinction between the power management versus device power management in Zephyr. So either the system power management, I would say, runs in the idle thread. So that's the thread that runs that if no other task is active. This will just put your CPU into a sleep mode if no task is to be scheduled until a specific deadline. And so you have the CPU waken up after that deadline. And the PM device is more like you want to disable some device more manually, more fine-grained. So you can just disable a device that's not used while others are still in use. That was about these two presentations, and we can move to the last one, which was a very nice overview of the new ZMS subsystem or system in Zephyr. So basically, it's a new storage system where you have that address the problem, or no, not really the problem. There are new technologies of non-volatile storage like magnetic RAM, resistive RAM, etc. They don't forcibly need some erase, and they still need some wear leveling mechanism. There are already some non-volatile storage system in Zephyr, but either they assume that you must always erase an entire page before writing, or they also have like a full file system. So you have, instead of storing key values, like you have an identifier and a blob that corresponds to that identifier. It's a tree hierarchy, like LittleFS. Or it doesn't scale to very dense memories because the address space is not large enough. So moving on to the next slide. The presentation goes in detail on how ZMS work. So basically you have the primitive are to store or retrieve some value, which is simply a binary blob. And the key is currently 32-bit integer. So the idea is that the ZMS will partition your flash or non-volatile storage into sectors, and the sectors contain data chunks that are written from the top, sorry, I have my screensaver, some allocation table entries which store metadata about the sector. Each of these ATE, so allocation table entries, have a cycle counter. And so this is the mechanism used to know what's the status of each sector. There are, I think, 3 status, as illustrated on the bottom right, which is closed. So the sector can only be read. The open status, so you can insert new data, and the erase status, which means this is the next sector you are going to write to. So as you can see, the cycle counter is used to determine which state the sector is. Like for instance, the orange one, you see that old cycle counter are 2. So in particular, the close ATE is the same as the other ones. The open one has a close ATE, which is less than the others, while the erased ATE, the erased sector has an empty ATE, which means the sector has been erased that is greater than the others. And so, mostly the presentation goes into detail about how this is managed, how the the where leveling actually works and how data is garbage collected. So this is I won't go into the details, but it's interesting to watch in the YouTube video. The main takeaways are that the performance of the ZMS subsystem is really sensitive to its configuration. So which sector size and number of sectors you actually define in the configuration, and which, if you enable caching, and I don't remember if you can choose some caching strategy, but like these are the different settings you can have, and they have a significant impact on the performance. And also, ZMS can be used as a backend for the Zephyr setting subsystem. So the Zephyr setting subsystem is a thing where you store some value associated to a string key this time. And so in this case, to store them in ZMS, you simply hash the settings key, which is a string, into a ZMS key. And you can have an access in early O1. And if you want to load all settings, which is a feature of the setting subsystems, you need some way of storing that. And so ZMS use a linked list to store all of that. Again, I would recommend to watch a presentation if you're interested, because there are lots of interesting details and keys on what's coming next. And if I remember correctly, he mentioned as well some tool to help you decide some ideal settings, like the sector size and count and stuff. And so that was the 3 or 4 presentation I found very interesting on my side.
And I will continue with some more Zephyr-related presentations. The first one is about upgrades. Zephyr is for really small devices, but it's not actually that small, so the firmware can be several kilobytes, and sometimes these devices are accessed over very slow connections like LoRaNet, in expensive connections. So it makes sense to make update images as small as possible. The obvious thing to do then is to do differential updates, so only transfer the differences between the current version and the new version. However, unfortunately, for a statically linked binary like what comes out of Zephyr, you very quickly get very big differences, even though the actual change is very small. So the example code that is shown here, it's not readable, but it's basically a function that hasn't changed. But if you look at the actual diff, it's quite large. And the reason of that is just very small changes in offsets for absolute jumps. So what Jordan worked on was a tool that can efficiently encode these small differences in a larger binary, where there are a few bytes which are the same, and then a few bytes which are different. And the key way that he does that is by developing a kind of virtual machine, which has an instruction which can be either copy or write. And so it either copies a number of values, or it writes a number of bytes. And so this is a very efficient way of representing that kind of difference. And then he developed tools to actually make that series of copies and writes, because you can do this in different ways, which leads to different compression rates. And so for the nice thing is that even though when you make small changes, even though the binaries are becoming quite different, the compressed one, with this technique, the compressed diff can still be relatively small. And so that would be in like less than a kilobyte for a 32 kilobyte update. Look at the video if you want more details. It definitely looks promising. And then the next talk is actually 2 talks, because these 2 talks came one after the other. with a small break in between. And they're about the same subject, namely Rust in Zephyr. Fortunately, the content was different enough to still be interesting. And so I'll just merge the key takeaways of those two talks here. So Zephyr, since release 4.2, which is just a few months old, it supports between quotes Rust. Now that doesn't mean that much. It just means you can include Rust code in your Zephyr build. And actually, support is actually a bit exaggerated because the examples don't even build. You have to use the mainline to actually get it to build. So integrated means you just use Whist still to build. So if you're not familiar with Zephyr, Zephyr has its own tool called Whist to control the builds, and that tool internally, amongst other things, calls CMake, and then the Rust integration from CMake will call cargo, and then cargo itself calls rustc. So it's a fairly long chain, but it works. Now, okay, just building something is not enough, of course. You also need to somehow interact with the rest of Zephyr. And so for that, it mainly uses a lot of pre-existing crates from other Rust-based OSs or for support systems for bare metal with Rust. A lot of that exists already, and so the Zephyr integration reuses that. And then there's some glue logic to be able to call Zephyr APIs from Rust code, and also vice versa to be able to call Rust code from Zephyr. So, for instance, to integrate with the Zephyr threads. So start a Rust-based thread from Zephyr. And so one of the talks, I think the first one, goes into quite a bit of detail about how to do that. But there's not that much API integration yet. So in most cases, you will have to develop your own glue logic. Now, unfortunately, although there were two talks about this subject, it looks like it's not used very heavily anymore because neither of them actually had a real application. They just did some experiments with it, but no real product based using Rust in Zephyr. So hopefully next year we will have a talk that mentions something like that. And then the next talk is going back to Linux. About kernel work. This was somebody from TI, so an employee of TI, working on integration of, adding support for two new PMICs to the kernel. So PMICs are power management ICs, and typically these PMICs are MFD devices, so multifunctional devices, because they also include a few other functions like GPIO and RTC. And so these two new PMICs, there's the 14 and the 15 on the left, they're very similar to the existing one, the 19, which already had a kernel driver, just a slightly different configuration, as you see in the table. And so the idea was to reuse the existing driver, but then first refactor it in a way that you can actually use a single driver for these three different PMICs. And so the goal was to have really tiny diff stats when adding functionality. And what you see in the bottom is how this could be achieved indeed. So first, a cleanup, which was actually a huge diff stat, where some things are abstracted in a different way in the driver. And then adding the new driver is not that much additional code. It's still a bit, as you see, 71 lines, 50 lines. It's not nothing. And actually, the main reason for that is because the hardware designers have been stupid. They did things like changing the meaning of some registers so that you actually have to twiddle different bits And so you need to add a lot of abstraction layers on top to manage which bit exactly to twiddle for which particular instance of the device. And so one important takeaway, since this is TI developing these drivers, they can now tell their hardware developers, don't do that anymore in the future, please. So yeah, this is one additional advantage of the upstream first policy, that hardware developers get educated about what they should and should not do. And then the next talk is one of the bootlean talks. So bootlean talks, or well, talks by bootlean people, they tend to be very similar in a sense. They always tend to be super technical and containing a huge amount of contents. And so this talk was no exception. So this talk is about the discovering non-discoverable hardware, so hot plug of non-discoverable hardware. So the use case is that you have some a main board, and then you have some add-on boards that can be plugged in. This concept is of course very old. We have this. It started with the Beagle board, and then Raspberry Pi also started doing that, and then almost all boards now have this concept of having plugs for add-on boards. Now, in most cases, currently, it's not hot pluggable, so it's basically the bootloader that takes care of those add-on boards, and the bootloader will load the device tree overlay and apply it when it boots, and and that's the way that problem is solved. But now, for this particular customer, they need hot pluggable boards, and so you need infrastructure for that, which doesn't exist at the moment. So there does exist in the kernel a mechanism to load the device tree overlay, but it's actually not usable because you need a driver that applies the device tree overlay, and there is no driver that does that. So this work was about adding the driver, such a driver, but also solving a lot of other things. So one thing that you need to solve is the device tree. That is basically you want to make a complete separation between the device tree of the add-on board and of the main board, so that it's possible to use the same device tree overlay for the add-on board, even if it can be plugged into different main boards. And so this is something useful actually even for non-hot pluggable devices, because currently you actually need, if you have a standard interface, a standard plug, like the Raspberry Pi plug is starting to be a standard. It's also used in other boards. Then you can have an add-on board that can still be used on these other boards, but it actually the overlay actually can't be used because the overlay refers to that particular I2C bus of the main board, and of course on a different main board is going to be a different bus, and that's shown in the picture on the bottom left. So for instance, in the left board, it's GPIO 1 pin 5, and that would be specified in the device tree overlay. But then on a different main board, it could be going through a GPIO expander, and so be a completely different device tree reference that needs to be used. So the way to do this is to have an explicit definition of the connector in using a they call it, I haven't put it on the slides, I forgot what they call it, but so a specific way of exporting the definition of this connector so that the overlay can use it. And so the overlay will only refer to the connector. So you see on the bottom, connector 1 active low, connector 1 active high. So it refers to that particular pin on the connector, it does not refer to anything on the main board. So this is one side, being able to specify this in the device tree in a more abstract way. And so this is on the way to inclusion in mainline. It's not far anymore. The other thing is hot plugging things which are not meant to be hot pluggable. So none of these things which are shown here, I2C, DSI, RQ, are meant to be hot pluggable. So they currently, the drivers are not ready for that. Or I2C is fortunately easy because you can just probe I2C devices dynamically. That functionality already exists, so okay, that works. For RQs, it's also possible. You just have to, the driver, the RQ driver has to support it, but again, RQs are typically GPIOs, so it's pretty standard. DSI is actually the big problem. So DSI, it's an interface for displays, and the display stack in the kernel, the DRM stack, does not actually support any flexibility in that part of the display pipeline. So this thing has to be reworked completely to make sure that it's possible for such a device to disappear at runtime. And there we're very, very far from upstream inclusion, because there are a lot of different subsystems involved, and DRM is a complex subsystem, and it really has to go into the core of DRM to be able to support that. That's the final talk I will to discuss in detail, but there are still a lot of other interesting talks that we attended. You see a list here. I'm not going to go over them. We will be working on a blog post, and these are the first ones that we are going to mention in the blog post. The blog post will actually be several blog posts because there's a lot we can talk about from this conference. And then, of course, there are still 250 talks that we did not go to. You can see all of those in YouTube. So there are 288 recordings in total on YouTube. One special mention, of course, is for this super interesting talk, MIDI2 in the real world by Titouan. Actually, I think it's kind of similar to the MindTech talk that Titouan gave a couple of months ago, but it goes a bit further than that. And then finally, Thomas is, the closing game. Yeah, that's an honorable mention as well. So ELC has a tradition of having a closing game. You see some pictures of how that happens. So it's basically Tim Bird, the guy that you see in the video, dresses up as something, and then he asks questions to the audience, and the audience, they put in a red or a yellow card to indicate their answer, and if you answer wrong, you have to sit down. So this way the participants are eliminated, and in the end, when there's just a few left over, they get a prize. Now, unfortunately, after 20 years, Tim is stepping back as the leader of the embedded Linux project. I'm not sure what the official name is. And somebody else, I forgot his name, is taking over, Jake something. And I'm not sure if that person is going to still do this closing game because he's much more shy and not outgoing like Mike. And then finally, Thomas, you still want to say something about the Buildroot developers meeting?
Yes.
So I would like to ask if we can
No, it's going to
quickly.
take just a minute. So just to mention that after the conference, we had the Buildroot dev meeting, which was a way also for Mike to see over to judge basically the Buildroot project we had ongoing starting from February of this year, and to see with the maintainer if there was anything we needed to change or to improve. And basically the main takeaway was that everyone seems to be quite happy with the work we did so far. So we will probably still continue working the same way as we did. And they were also really open to collaborating more with them, asking them directly more questions instead of doing it on our own, so that we can possibly also try to decharge a bit of the work, the question we try to solve by ourselves to them directly. So I won't go into too much detail because it's already late and people are starting to get hungry, I guess. Hugo, I guess you will do the
Yes, words. Thank you very much, Thomas. Also, thanks to all the presenters, Arnout, Titouan, Thomas again, and Charles-Antoine. Frankly, I'm a little bit overwhelmed by all the topics that have been discussed, such as security, a very nice comparison here and there between how things are approached between Linux and between Zephyr. I believe it was really interesting. I'm not going to talk too long because we're already over time, but I'm very happy that we're resuming our activity with Mind Technical Talks, and we will keep you guys posted about the next Mind Technical Talk next month. Thank you very much, guys.
Thank you.